concrete chemistry altered by carbon dioxide injection to achieve 13% strength gain. MIT researchers used laser imaging to uncover the rapid reactions inside CO2-injected cement. For years, companies have injected carbon dioxide into concrete to trap emissions and improve early performance. The construction industry embraced the approach even though researchers could not fully explain why it worked. Now, scientists at MIT say they have finally watched the chemistry unfold in real time. Using laser-based imaging, the team captured the rapid reactions that occur when carbon dioxide meets fresh cement paste. The observations revealed a temporary chemical pathway that reshapes how the material hardens. The process produces a more evenly distributed binding structure and boosts early strength. The findings could help engineers fine-tune low-carbon concrete technologies already entering the market across the United States. The work also offers a clearer picture of how cement, one of the world's most carbon-intensive materials, can store captured carbon while maintaining performance. Tracking hidden reactions. Researchers from MIT's Concrete Sustainability Hub and Department of Civil and Environmental Engineering used Raman confocal microscopy to monitor cement samples continuously during their first 24 hours of curing. The technique identifies materials by analyzing how laser light interacts with chemical bonds. Each compound leaves behind a distinct spectral signature. Previous studies relied largely on theory and indirect measurements because the reactions happened too quickly for conventional tools to detect. We've used Raman spectroscopy to better understand some of the most interesting materials in history, from the Dead Sea Scrolls to ancient Roman concrete, Associate Professor Admir Masic said. Cement paste may seem less glamorous in comparison, but pointing a laser at CO2-injected cement paste as it hardens allows us to visualize things that haven't been seen before. The team discovered that carbon dioxide initially captures calcium released during cement dissolution. That temporary shift slows normal hydration and changes the environment inside the paste, the disappearing template. As calcium becomes tied up, dissolved silicates spread through the material and assemble into an interconnected silica gel network. The gel survives only briefly. Once the injected carbon dioxide fully mineralizes several hours later, standard hydration resumes. Calcium hydroxide forms and immediately reacts with the silica network. That reaction produces calcium silicate hydrate, or CSH, the compound responsible for cement's binding strength. Unlike conventional cement, however, this new CSH develops throughout the material rather than clustering around cement particles. At first, the fleeting nature of the silica gel looked like a fluke in the Raman data, graduate student Marcin Hajduczek said, but it quickly became clear that its sudden disappearance was a consistent, undeniable feature of every CO2-injected sample. Stronger concrete, new possibilities. The altered pathway leaves behind a more uniform internal structure. In tests, cement paste containing carbon dioxide equal to 1% of cement weight achieved an average of 13% higher compressive strength after 24 hours than reference samples. The findings also challenge previous assumptions. Researchers found calcium carbonate particles acted more like spectators than drivers of strength development. We've been injecting CO2 into cement products for years without fully understanding what it was doing inside, Masic said. Now that we understand the mechanism behind the improved performance, we can start to control it. The researchers caution that dosage remains critical. Excessive carbon dioxide can lock away too much calcium and disrupt beneficial reactions. Even so, the work offers engineers a roadmap for designing stronger, lower-carbon cement products for future infrastructure projects.